Let me show you how to cut out a circle using a pen-shaped cutter and a compass. So first I draw a circle with a pencil. And now, using a cutter attached to my compass in place of a pencil, I try my best to trace out the pencil-drawn circle to cut it out of the sheet of paper. But notice that since this circle is small, my cutter instead spiraled inwards to form something that looks like the slice of a roll cake. Now let's try with a medium circle. Same procedure, first draw it with a pencil, then trace it out with a cutter. And this time, the cutter was able to trace out the circle I've drawn almost perfectly. Lastly, let's try this on a big circle. So now, what happens? The cutter spirals outwards so that its blade is now further away from the compass needle. I've repeated this process for circles with radii measuring from 2 to 9 centimeters. Just for convenience, we're using only integer values for circles radii here. I've also colored pencil traces purple and cutter traces orange, so now you can see for each circle where I started running my cutter and how far off the circle circumference each cutter trace ended up. As expected, some of the time the cutter spirals inwards. Sometimes it spirals outwards, while the rest of the time it pretty much stays on the circle. So, what if I want to model these observations? Like if I draw a circle and I'm about to cut it out, how can I predict whether or not my cutter and compass will misbehave, and if they will, by how much? But before we answer those questions, I'm telling you that I'm excluding the two largest circles with radii of 8 centimeters and 9 centimeters because at those sizes my compass and cutter no longer behave in the same pattern that we have observed for smaller circles so far. So now let's dive right in. So here I have a circle with a radius equal to 6 centimeters. As you can see, the cutter spiraled outwards to be 6.2 centimeters away from the compass needle over the span of a reflex angle, reaching what I've labeled to be the point of largest deviation. So if I measured out that angle using a protractor, I find that the radius of the spiral traced out by my cutter increased by 0.2 centimeters after traveling around that circle 334 degrees. Now, let's punch some numbers into a calculator. Let's see, converting the angle measured to radians gives us about 5.83 radians. So that means the rate of change of the radius as this angle varies is equal to 0.2 centimeter divided by 5.83 radians, which gives 0.3431 centimeter per radian, on average from the starting point to the point of largest deviation. And if I repeat this process for all my circles, this table of values is what I get. So as you can see, the values of delta r over delta theta generally increase with increasing radius, meaning that as the circles get larger, the tendency for the compass and cutter to spiral outwards generally grows, which is consistent with our original observations. So now, plotting all the pairs of values, r, delta r over delta theta on the Cartesian plane, we can observe that there is, very roughly, a linear relationship between the starting radius of the circle that I want to cut out and the rate at which my cutter spirals outwards as I attempt to run it along the circumference. Note here that the negative rate of change indicates that the cutter tends to spiral inwards for a circle of that radius. Now I can get Desmos to calculate for me the best fitting linear equation that describes this relationship. However, as a word of caution, What I'm trying to build here is not a linear regression model, as there are obviously too few data points for me to pull that off. However, it can still be useful and interesting to explore how these two variables R and delta R over delta theta are related. So here's the equation. Delta R over delta theta equals 0.337 times the starting radius R of 0, meaning the radius of the spiral at theta equals 0, which is the starting point, minus 0.1566. Using this equation, we can now predict the rate of change of our spiral's radius as we run our cutter around a circle based on its starting radius. This in turn enables us to express R as a function of theta because, as we have seen earlier, the cutter usually spirals further and further away from the circle's circumference as we move around it. I'll do a couple of examples. When R of 0 equals 2, R of theta equals 2, which is the starting radius, plus delta R over delta theta times theta. I should have written a plus sign there. And remember, this rate of change is given by the best fit equation times delta theta. But since theta is just 0 at the start, then theta minus 0 is just theta. So now plugging this into the calculator, we get R of theta equals 2 minus 0.892 theta, which makes sense since the longer we move around the circle, the deeper the cutter spirals inwards for the circle of radius 2 centimeters. Repeating this process for when R of 0 equals 3, we get R of theta equals 3 minus 0.555 theta. We can continue doing this until we get all the functions R of theta for each starting radius. And now I'm going to switch over to a polar graphing calculator to see what we've done. Let's start with R of 0 equals 2. So R equals 2 minus 0.0892 theta. Let's just restrict theta to the interval 0 to 4 pi so it doesn't get too messy. So here's what we get. A curve which spirals rapidly inwards. Perfect. Now let's repeat for R of 0 equals 3. And this curve, too, spirals inwards, but not as rapidly as the curve corresponding to R of 0 equals 2. I've typed in all of our functions, plus the coordinates of the starting point for each of our spirals, which are all of the form R of 0, 0, meaning R equals the starting radius, like 2 for example, and theta equals 0. So now let's visualize each of these curves in turn. Starting radius 2, starting radius 3, starting radius 4, still spiraling inwards, starting radius 5, pretty much a circle, starting radius 6, spiraling outwards, and finally starting radius 7, spiraling outwards the most rapidly. So far, we have successfully built a model that achieves what we set out to achieve. Our linear model correctly predicts that the cutter we saw at the beginning will spiral into circles of radii smaller than 5 centimeters, cut out circles of radius around 5 centimeters, and spiral outwards for circles of radii greater than 5 centimeters. But is a linear model really the best that we can build? Well, it turns out that there may be better alternatives. Consider this. Since circles with smaller radii tend to spiral inwards, whereas those with larger radii tend to spiral outwards, what type of function does that remind you of? Try thinking of a function that makes small inputs even smaller and big inputs even larger. Does that remind you of the exponential function? Specifically, we can model our earlier observations using an exponential function of theta, with the starting radius R of 0 acting as its base. Now, strictly speaking, a function like this would be a multivariable function since we're looking at a variable r that varies depending on two other variables, namely the starting radius of the circle and the angle by which we have traveled around the circle. But let's just keep it simple for now and treat r of theta as a single variable exponential function of theta while treating our starting radius r of 0 as a parameter. Let's start with r of theta equals r of 0 raised to the power of theta. In this case, if you start with a circle of radius greater than 1, r of theta will increase with increasing theta, meaning that as you move around your circle, your cutter spirals outwards. If, on the other hand, you start with a circle of radius smaller than 1, r of theta will actually decrease with increasing theta, meaning that your cutter will spiral inwards as you move around your circle. But since we have observed earlier that the starting radius for which r of theta remains approximately constant is 5 centimeters, not 1, we'll need to transform this function to build a more suitable model. Finally, what if our cutter spirals away from the circumference of our circle, not just based on the starting radius, but based on the current radius of the spiral that it's on at every point in time? In other words, what if the rate of change of r of theta with respect to theta depends on its own value as you move your cutter around the circle at constant speed? Well, it turns out that even such a simple activity as cutting out circles with a compass and a cutter can give us an example of what differential equations are for. Pretty unexpected. So now the rate of change of r with respect to theta equals some function of r. Now a differential equation like this will require some special technique to solve, but since we don't know what this function of r on the right hand side is, there is currently no way for us to find r of theta. Let's save that exploration for another time. I hope you enjoyed this video and that this exploration has inspired you to look for ways to apply your mathematics knowledge to explore some observable phenomena even within your daily life. Because really, you don't need to look too far for good ideas.